now we actually start to talk into new things and how to build superscalar processors, things that exploit ILP, instruction level parallelism, things that run at really high clock frequency or multiple cores, and advanced techniques. So before we start talking about superscalars, there's a piece of nomenclature we need to introduce that sort of goes hand in hand with the data hazard talk that we had before. But I didn't introduce it there, but I need to introduce it now before we go on to actual superscalars. So let's consider some example instructions here where register I, register J, you operate out of and you put it into register K. And we're going to look at different types of dependencies. And we're going to name them. So the basic dependency here is a read after write hazard, or a read after write dependence. So in this example here, if time goes down, this operation here is going to store into register 3, and then this instruction here is going to read from R3. So you need to sort of temporally make sure that this happens before that, because you need the value here. OK, so we talked about this already in our data hazards. This is the most classic data hazard here, a read after write hazard. Let's look at something a little bit more, a little bit less intuitive. Let's look at a hazard where this instruction here reads register 1, and the next instruction writes register 1. OK, that should be no problem. That sounds great. Well, today, we're going to give an example of a pipeline where this is a problem, or could potentially be a problem. So, if you do everything in order, and your instructions just sort of slowly flowing down the pipe, and you're only executing one instruction at a time, you're going to execute this, and then that, and you're going to read register 1 here, and then like a whole lot of time later, you're going to write register 1, so nothing bad happens. But if you start to execute instructions either out of order, or if you start to execute multiple instructions at the same time, you can start to come in some problems. But we're going to name this a write after read hazard. So what that means is we have a write that temporally in the program order is happening after a read of that same register. So and this is usually called anti-dependence. And we need to maintain these when we go to execute our programs out of order and sort of throw everything into a big bucket and try to pull out instructions. OK, output dependencies. This is actually something that you could possibly even think of having happen on a simple sort of in-order processor core if you do write back to the register file from different stages. So let's take an example. If you have a multiplier, like in your lab, which is going to write at the end of the pipe and have a very, very high latency, and then you have a instruction like an add, which is, let's say, you try to write to the register file early, you might actually write this instruction's result to register 3 before that instruction's results. If, let's say, this instruction here is a long latency operation, something like a multiply, and this is like an add. So we're going to call that a write after write dependency. And we need to maintain the order here that this gets written first, and then this gets written. Because if you flop those two results or interchange those two results, the next thing that goes to read R3 is going to get the wrong value. So that's pretty important. And it's called an output dependence. OK, so last question. Is there such a thing as a read after read dependence, or read after read hazard? So superscalar processors. So far, we've been limited to processors that can only get a clock per instruction greater than or equal to 1. Superscalar processors will allow us to execute multiple instructions at the same time, and will move us into a new class here of the clock per instruction potentially below 1. It's at least fundamentally possible. Now, there might be other things that cause our clock per instruction to actually still be above 1, but we can get higher performance by executing multiple instructions in parallel. I wanted to introduce a nomenclature here that's the reciprocal of instructions per, or clock per instruction, which is instructions per clock. We just move them and rename it. Sometimes people say IPC, and it's the reciprocal of CPI versus CPI. Clocks per instruction equals 1 over instructions per clock. So just be aware of that. Sometimes we'll be using those terms different interchangeably in this class. OK, so what types of superscalar processors can we talk about? There's lots of different types. There's in-order machines and out-of-order machines, roughly. And what in-order machine means is the machine, or the processor, is still trying to execute instructions in program order. Well, you don't have to do that. You could actually think about sort of taking apart the program and executing them out of order as long as you're trying to sort of preserve the different hazards, data hazards. And something like your Pentium processor. So I'm going to pass around here a roughly Pentium 2 class processor. It's actually an Intel Celeron Pentium. The Pentium 2 version of the Intel Pentium Celeron is a out-of-order 3-wide superscalar. So it can execute 3 instructions at a time. For instance, another example is the original Pentium. The old Pentium, when the original Pentium came out, that was a 2-wide machine. So it could execute 2 instructions at one time, and it was in order. So we can think about these different notions.